Good evening.
Good evening, sir. You can start, sir.
Hello, can you see the screen, everybody? Yeah. Hello, can you hear me?
Yes, sir. Good evening, sir.
Yeah, good evening. Others?
Yes, sir.
Yeah. The next chapter, solutions and colligative property. Solutions and colligative property. The first chapter, solids, I think we have done it maximum possible. You can practice those. Now the second chapter, solutions and colligative properties. The last part of the topic is colligative property. We will learn colligative properties in the later stages. Now we'll try to understand the concept of solution. This also we have learned it in the first chapter. So we will continue with that, concentration. What do you mean by solution? What do you mean by heterogeneous, homogeneous solution? All that we will learn. A solution is a mixture in which substances are intermixed so intimately that they cannot be observed as a separate component. So it's a complex definition. A homogeneous mixture of two or more components will be called as a solution. See here, they've so told a substance which are intermixed so intimately that they cannot be observed as a separate component. Salt and water. Salt and water. You have two components. You get salt solution, or we call it as aqueous solution of salt. Now, salt is one component, water is the second component. In aqueous solution of salt, it appears just like water. We cannot see separately the salt particle or the water particles. That is what they are telling. It's called as what? Homogeneous mixture. Homogeneous mixture of two or more components will be called as a solution. Now, they are introducing two terms here. One is dispersed phase. The other one will be called as dispersion medium. Dispersed phase, and the other one will be called as dispersion medium. Now, dispersed phase is generally a solute. Dispersed phase or a substance which is to be dissolved is called a solute, while the dispersion medium in which the solute is dispersed to get a homogeneous mixture is called a solvent. So we have to understand two terms here. One is dispersed phase and the other one is dispersed medium. Now, dispersed phase is otherwise called a solute, and dispersed medium is otherwise called a solvent. Now, for an example, if you take steel, now in the steel, the major proportion is what? Iron. And very little amount of carbon will be present. Both are solid. So I've taken this as an example. So carbon will be called as dispersed phase and iron will be called as dispersed medium. Even in steel is a solid. We will have to learn different types of solutions in later stages. So what do you mean by dispersed phase? Now, for an example, one more example, if we take the atmospheric air, this atmospheric air is made of what? Atmospheric air is made of what?
Different gases.
What are the major gases?
Carbon dioxide, oxygen.
Nitrogen.
And oxygen. Majorly, it is what? 21%, around 21% oxygen and 79% nitrogen. Now, since nitrogen is in large scale, nitrogen will be called as dispersed medium. And oxygen is in small percentage. Therefore, this oxygen will be called as dispersed phase. So oxygen will be called as a solute and nitrogen will be called as a solvent. This is a gas. Air is a gas. But still we call this a solution. We will learn about it a little later in detail. So that is why we are introducing the terminologies here, dispersed phase and dispersed medium. What is dispersed phase? Substances which are in smaller quantity, which is distributed or which is dissolved is called as dispersed phase. A chemical substance which is taken in large quantity, which contains the dispersed phase is called as dispersion medium. And dispersion medium is otherwise called as a solvent here. So far, is it clear?
Yes, sir.
Everybody followed? Yes. Now we have to understand a term called as solubility. Now, if you take a small amount of salt, a pinch of salt, and put it in water, what happens? The salt dissolves. We say salt is soluble. But how much, what do you mean by the term solubility here? Solubility of a substance may be defined as the amount of solute dissolved in 100 grams of solvent to form a saturated solution at a given temperature. What do you mean by saturated solution? Now, you take salt and you take 100 ml of water and you add a pinch of salt into it, a tablespoon of salt into it otherwise. When you add a tablespoon of salt into 100 ml of water, the salt will completely dissolve. Second time you add 100 ml, second time you add one more teaspoon. What happens? The salt will completely dissolve. The third time you add, it dissolves. The fourth time you add, what happens is you will observe the salt particles settling at the bottom. The salt particles settling at the bottom. So these kind of solutions are called as saturated solution. A solution in which further dissolution of a salt is not possible. Those kind of solutions are called as what solutions? Saturated solution. So one we have been learning from last chapter. And the third is saturated solution. Dilute solution, concentration of the solute is minimum. Concentration of the solute is minimum. Concentrated solution, so concentration of the solute will be little more, max. And here it will be what? Excess. Saturated solution, the solute concentration will be what? Excess. That is why I told you, if you take salt, a pinch, and add it into water, it forms a solution, dilute solution. If you add a teaspoon of salt into water, it forms a concentrated solution. You can taste and see, it will be highly salty. If you add a pinch in water and taste, it will not give you the saltiness. But if you add a teaspoon of salt in 100 ml water, and if you take more bottom, those kind of solutions will be called as a saturated solution. Now, what's solubility? Solubility of a substance may be defined as amount of solute dissolved in 100 grams of solvent to form a saturated solution at given temperature. So the weight of solute dissolved in 100 grams of any solvent so that we get a saturated solution is called as what? Solubility. Now, for an example, if I say, maybe if I say 30 grams of salt, if I put 30 grams of salt in 100 ml of water, some of the salt particles settles at the bottom, then we say 30 grams of salt as what? The solubility of the salt solution. Did you understand this? Follow?
Yes, sir.
Yeah. Now, saturated solution, as already I told you. What is saturated solution? A solution which contains at a given temperature as much solute as it can hold in the presence of a dissolving solvent. I clearly told you a solution in which further dissolution of a solute is not possible. Those kind of solutions are called as saturated solutions. A solution in which further, now you see, I told you first time you add tablespoon of salt, it dissolves. Second time you add, dissolves. Third time you add, it dissolves. Fourth time when you add, I told you it settles at the bottom. Now, fifth time if you add the salt, do you think it will dissolve or it will settle? Do you think it will dissolve or settle?
So settle.
In the class, it will settle. In solute is not possible further. Those kind of solutions are called as saturated solution. A solution, maybe I'll write here in simple terms, a solution in which further dissolution of solute is not possible. Those kind of solutions are called as saturated solutions. Clearly, it says a solution which contains at a given temperature as much of solute possible, as much of solute it can hold in the presence of a dissolving solvent. Or you can write this as a definition. This seems to be simple. A solution in which further dissolution of a solute is not possible is called as a saturated solution. Now, the next point here is any solution which contains less solute than would be necessary to saturate it, those kind of solutions are called as unsaturated solution. Now, firstly, if I take 100 ml of water, if you add 10 grams of salt or 1 teaspoon of salt, it dissolves. That solution is an unsaturated solution because furthermore solute can be added to it. Therefore, the solute present here will be less when you add only 1 tablespoon. This is for an illustration. Don't think it is practical, all right? To make you differentiate between saturated and unsaturated, I'm telling. Followed, students?
Yes, sir.
Yeah. When the solution contains more solute than it would be necessary to saturate, then it is termed as supersaturated solution. If the solute is in excess, then we call that as a supersaturated solution. So few terminologies we learned today, that is dispersed phase, dispersed medium we learned water solubility, amount of solute dissolved in 100 grams of a solvent to form a saturated solution, that is called as solubility. So wait, see, it depends. It depends. See, now if I take salt, if I say 30 grams, if I take sugar in 100 ml of water, sugar may take 40 grams also. So 40 grams of sugar will be called as for solubility of the sugar. Are you following what I'm telling? And different salts are there. All inorganic salts you would have done in the laboratory. So different salts. So different salts will have different solubility. Clear?
Yes, sir.
Others are not participating. Rupashri, Ritika, Dhanushri, Dhanalakshmi. Others are not participating. All right. Now, kinds of solutions. See, this is what important now. Kinds of solution. All 3 states of gas, liquids, and solids may behave either as a solvent or as a solute. So far, what we have learned till 11th, till school level is when we say solution, it is only liquid. Now they are telling all 3 states of matter, gases, liquids, and solid, all these 3 may behave like a solute or a solvent. Depending on the state of solute or solvent, mainly there may be following types of binary solutions. See the following types of binary solutions. 9 types of binary solutions we have. The first one is a solute is a solid and solvent is also a solid. Solute is called as dispersed phase. Solvent is called as what? Dispersed medium. See, dispersed medium is something which is in large quantity. And solute is something which is in dispersed phase is something which contains smaller quantity, or dispersed phase is otherwise called a solute. It's marked here. Now, I took an example. Steel, I took an example. Steel, it contains carbon and iron, I told you. It also contains other metals like nickel and iron. Nickel will be small quantity, iron will be in large quantity. So nickel and iron can be called as an alloy because mixture of 2 metals which appears to be as a single metal will be called as an alloy. Yes or no?
Yes, sir.
Yes or no? Yes. Now see, solute is a solid and solvent is also a solid. Dispersed phase is a solid, dispersed medium is also a solid. So those type of solution is called as solid in solid. Those kind of solutions are called as solid in solid. Example, alloys, any alloy for that matter. Amalgam. Amalgam means any metal dissolved in mercury. See, all the metals will dissolve in mercury. Sodium, if you dissolve in mercury, it's called a sodium amalgam. So amalgam is nothing but mixture of a metal and mercury will be called as an amalgam. So amalgam is an example for a solution of the type solid in solid. Next, you can see the solvent is a solid and the solute is liquid. Now, liquid in solid, that's the name of the solution is called as liquid in solid. Hydrated salts. When I say hydrated salt, copper sulfate dot 5H2O, we write. This is hydrated salt. See, water is present. Water is a liquid. It's present in copper sulfate. Small amount of water is present in copper sulfate. So liquid is present in a solid. Therefore, that kind of solution is called as liquid and solid. An example for that is hydrated salt. Following.
Yes, sir.
Yeah. The third is the dispersed medium is a solid and dispersed phase is a gas, or the solute is a gas and solvent is a solid. So those kind of solutions are called as gas in solid. Gas in solid. So dissolved gases in minerals. So in minerals, we will have dissolved gases. Those are the examples for a solution of the type gas in solid. Dissolved gases in minerals. Next is solvent is a liquid. Dispersed medium is a liquid. Dispersed phase is a solid. So it is called a solid in liquid. Name of the solution is solid in liquid. Example, salt is solution in water. Is a solid. Water is a liquid. Salt in water, not salt is solution in water, salt in water. So it's an example for solid in liquid. Salt is a solid, water is a liquid. So it will form solid in liquid solution. Now next, solute is a liquid, solvent is all. Alcohol in water. Alcohol is also liquid, water is also liquid. So alcohol in water. Liquid. Next is liquid is a solvent. So those kind of solid drinks, all Coke, Pepsi, soda, all those are gas in liquid. Carbon dioxide gas in water. Aerated drinks are nothing but carbon dioxide in water. Carbonic acid will be formed. We'll come to that a little later. In liquid. Now the solute
Excuse
or
me,
dispersed
sir.
phase is solid. Yes, yes. Yes, ma'am.
Sir, your voice is breaking.
I don't know. All right, ma'am. I'll check. Ma'am. I'll check.
Sometimes it's not audible, sir.
Are you there now? Can you hear me now?
Yes, sir. Now you are audible.
Yes, sir. Yes, sir. Now you're.
Okay. Some issues maybe with the network. Can't help it. Now the seventh type of solution is solid is a dispersed phase and dispersed medium is gas. So those kind of solutions are called as solid in gas. Iodine vapors in air. Solid is the dispersed phase and gas is a dispersed medium. So palladium over hydrogen over palladium. So palladium is a metal which is a solid and dispersed phase. Next is liquid is a dispersed phase and gas is a dispersed medium. So those kind of solutions are called as liquid and gas. Mist, humidity in air. Mist is nothing but water molecules in the atmospheric air is called as mist. Likewise, the last type of solution what we have is gas is a dispersed phase and gas is a dispersed medium. Those kind of solutions are called as gas and gas. An example is atmospheric air. I gave you the example in the beginning of the class also. So we are not concluding that solution is only solid and water or a salt and water. No. So a solution can be of different types, different types of solutions. So solute can behave, I mean, the solid can behave like solvent, or sometimes solid can behave like solute. It depends. Excuse me. All right. Depending on the nature or depending on the state of solute and solvent, we have 7 types of binary solutions. Not 7, 9 types of binary solutions. Sorry. Binary means two components. So this is important. But in this chapter, we will be learning with respect to only solutions in liquid state. That is solid and liquid. We will be learning only this. We will learn about it in detail. Now coming to, we have learned that, just to brush up, I'm giving you this because we need this. We need this calculations to work out the problems in the chapter solutions. That's why weight percent means weight of solute divided by weight of solute divided by weight of solution into 100. That's called as weight percent. We have learned both are in weight. Solute is also in weight, solution also in weight. Volume percent, volume of solute divided by volume of solution into 100. That's called as volume percentage. Now, for an example, if I say take alcohol in water, if you take 10 ml, if you take water 100 ml, then what's the percentage? 10 divided by 110 into 100. That will give you the percentage. Volume of 100 alcohol, volume of the solution into 100. So weight to volume percent, weight to volume, weight of solute per 100 ml of solution. So it's clearly given weight of solute divided by weight of solution into 100. That will be giving you volume of solution. Sorry, this is volume of solution. Volume of solution into 100 gives you volume, weight to volume percent. We have worked a lot of problems based on this. We will learn. No, in solids, we have not learned, right? What I was doing. Okay, anyways. Now, next is parts per million. Parts per million or parts per billion, ppm or ppb. 1 billion is 10 to the power 9 parts. Now, what's the parts per billion? Okay, it's number of parts of solute present in 1 million part of the solution, or number of parts of solution present in 1 billion part of solution is called as parts per billion. It is parts per million is independent of temperature. It does not depend on temperature. All right. The next, I don't know why there's an issue here. Can you hear me?
Yes,
Can you,
sir.
yeah. Why?
Yes, sir, we can hear you, sir.
Yeah. But there's some problem with the network today. See, we will talk about this normality, molarity, all that. Few minutes time. All right. So, all right, normality. What is normality? It is defined as number of gram equivalent weight of a solute present in 1 liter of the solvent. Okay, number of gram equivalent weight of a solute present in 1 liter of the solvent. Now, how do you calculate the equivalent weight? Equivalent weight is calculated by the formula atomic mass by valency. If it is an element, it is atomic mass by valency. Or if it is an acid, equivalent weight of an acid is calculated by the formula molecular weight divided by basicity. Molecular weight divided by basicity. I will tell you what is basicity. Now, equivalent weight of a base is given by the formula molecular weight divided by acidity. Now, for an example, if I take HCl, this HCl will react with NaOH to form NaCl and water. This is a very simple known reaction. Now, if I ask you a question, in HCl, how many replaceable hydrogen is there? How many replaceable hydrogen is there?
So one, sir.
One. So one replaceable hydrogen is there. Therefore, we say the basicity of HCl is 1. So basicity means Number of replaceable hydrogen is called as basicity. Now tell me, if I have H2SO4, H2SO4 will require 2 moles of sodium hydroxide to give sodium sulfate and water. Now you tell me how many replaceable hydrogen sulfuric acid has?
2, sir.
So therefore, basicity of sulfuric acid will be 2. Therefore, basicity of sulfuric acid will be 2. Likewise, if I take phosphoric acid, H3PO4 is phosphoric acid. So how many replaceable hydrogen we have? 3 replaceable hydrogen. Therefore, the basicity of phosphoric acid will be 3. So what is basicity? Basicity is defined as number of replaceable hydrogen present in an acid is called as basicity. I hope that you followed this. Correct? Yes?
Yes, sir.
Yeah. Now just observe. I'll take few examples again. HCl. What's the molecular mass of HCl? 1 plus 35.5. So molecular weight of HCl is 36.5. Molecular weight is nothing but sum of the atomic masses will give you molecular weight. This is molecular weight. Tell me, as per the formula, what is the equivalent weight of HCl? What is the equivalent weight of HCl? It is 36.5 divided by, what's the basicity of HCl?
1.
1. So it will be again what? 36.5. That means for the acid whose basicity is 1, their molecular weight is equal to equivalent weight. Can we conclude this way? Yes? Yes or no?
Yes, sir.
Now, if I take sulfuric acid, the molecular weight of sulfuric acid is 98. What will be the equivalent weight of sulfuric acid? What will be the equivalent weight of sulfuric acid? 98 divided by, what's the basicity of sulfuric acid?
2, sir.
So 2. Therefore, it will be what? 49. Therefore, the equivalent weight of sulfuric acid is 49. Did you understand this? So far, you have understood?
Yes, sir.
Now, we are going to define what is normality. I'm giving you a formula to calculate normality a little later. Now, it is defined as number of gram equivalents of solute present in 1 liter of the solution. 1 liter of the solution. The unit for normality is gram equivalent per liter. So what is the definition of normality? It is defined as number of gram equivalent weight of solute present in 1 liter of solvent. My question is very simple. Think and answer me the question. If I take 36.5 grams, this is wrong, but for illustration, I'm giving you. If you take 36 grams of HCl in 1 liter of water, what will be the normality? What will be the normality of HCl? What will be the normality of HCl? We understood what's the equivalent weight of HCl. What is the
Yes, sir.
36.5? So 36.5 grams will be called as gram equivalent weight. So 1 gram equivalent weight, that is 36.5 grams of HCl in 1 liter, will be called as what normal? Called as what normal?
1 normal, sir. 1 normal.
Okay, if I ask you a question like this, 73 grams of HCl. 73 grams of HCl in 1 liter. What will be the normality? Huh?
2 normal.
2,
2 normal.
because double I gave you. Correct?
Yes,
If I give you like this 73 grams of HCl in 2 liters of water, what's the normality?
1, sir.
So 1.
1. Good. So you have understood the concept of normality. Now you think and answer me the question. Think and answer me the question very carefully. Okay. Now, what is the normality of 98 grams of sulfuric acid in 1 liter? This is again wrong. I am telling you, this is for illustration. What will be the normality of HCl? What is the normality of HCl? What is the equivalent mass of...
1, sir.
no, sorry, sulfuric acid. What's the equivalent mass of sulfuric acid?
So it's
49.
1 normal. So
49, no? That means 98 grams is how many equivalents?
Double the 49.
Yeah, double the 49. That means 2 gram equivalents. 2 gram equivalents in 1 liter will be called as how many normal?
2 normal, sir.
Followed or not?
Yes, sir.
Followed, sir.
Yes. So what's the, now I'll give you the formula to calculate the normality. All right. You remember this formula to work out the problems. A lot of numericals will be there. Different types of numericals you have to understand. So normality can be calculated by the formula weight in grams divided by molecular mass into 1000 divided by volume of the solution. We'll work out some problems little later. So normality is given, not molecular weight. Sorry, I made a mistake here. It's not molecular weight. It is equivalent weight. Normality is what? Weight in grams by equivalent weight into 1000 divided by volume of the solution. Because whenever you want to calculate normality, we need to take the weights in terms of equivalent weight. All right. Normality changes with temperature since it involves volume. So when you heat the solution, what happens? The volume expands, volume increases. Since volume increases, the normality also will change. These 2 points you have to remember. Now, when solution is diluted X times, its normality decreases by X times. When solution is diluted X times, its normality decreases X times. What does it mean? I take one normal solution, one normal of 100 ml solution. Any solution, one normal, 100 ml. All right, listen to this. All the others are there? Please
Yes, sir.
participate. Please participate.
Yes, sir.
I'm taking one normal in 100 ml. Any solution, one normal. To this, I am adding 1000 ml of water. 1000 ml of water. That means what happens? The concentration will be diluted or not? Yes or no? Solution will be diluted or not?
Yes, sir.
How many times the solution will be diluted? And what will be the concentration of this? What will be the concentration of the solution? I am taking one normal solution of 100 ml. To that, I am adding 1000 ml. So what will be the decrease in concentration? See here, when a solution is diluted X times, its normality decreases by X times. So 100 ml is the solution, what is taken. To that, how many times I am adding water? More. 10 times I'm adding water more. So when I'm adding more 10 times water, it means I'm diluting it by 10 times. When I dilute it by 10 times, the concentration has to decrease by 10 times. No? So if the concentration decreases by 10 times, what will be the concentration? What will be the concentration? Will it be 0.1?
Yes, sir.
Others, nobody is participating. Only 2 of them I'm able to listen. That's fine. That's fine. All right. Did you understand this normality concept? How to calculate the equivalent weight?
Yes.
Similarly with the base also. Okay. When we talk about base, we need to talk about acidity. Now, for an example, I'll give you one such example also for that. NaOH. NaOH will react with HCl to form NaCl. Same reaction, I wrote it in the reverse order. Now, how many OHs are there? Sodium hydroxide contains only one OH. Therefore, acidity of sodium hydroxide is 1. If I take calcium hydroxide, what is the acidity of calcium hydroxide? Since we have 2 OH, the acidity will be what? 2. Yes, acidity will be 2. So these 2, many formulas I gave you today. So please concentrate and see this class repeatedly, and then you will understand better. Now we are going very fast because similar to normality only is molarity. Molarity of a solution is the number of moles of solute. Number of moles of solute. Number of moles of solute per liter of the solution, or number of millimoles of solute per ml of the solution. So you don't worry about this. Number of moles of solute per liter of solution. Unit for molarity is mole per liter or mole per decimeter cube. Now, you know what's a mole? How do you calculate a mole? Weight in grams divided by molecular mass will be called as mole. If I say calculate the number of moles of 5.85 grams of NaCl, 5.85 grams of NaCl. So how do I calculate the number of moles? What's the given weight? Given weight is 5.85. What's the molecular mass of NaCl? 58.5. So divide. Therefore, 5.85 grams of NaCl will be how many mole? 0.1 mole. Are you following?
Yes, sir.
Yes. So number of moles is calculated by the formula. Number of moles is calculated by the formula weight in grams per molecular mass. So if I have 1 mole, so if for that example, 58.5 grams of NaCl, if we take in 1 liter of water, then the molarity of the solution is 1 molar. Then the molarity of the solution is 1 molar. All right. So molarity, we take what? Moles. Normality, we take equivalent mass. So what's the formula to calculate molarity? I'll give you the formula. Molarity is most common way to representing the concentration of the solution. So laboratory, we will generally represent concentration in terms of what? Molarity. Molarity is dependent on the temperature. Molarity is inversely proportional to temperature. Inversely proportional to temperature. As temperature increases, molarity decreases. Now, when solution is diluted X time, its molarity decreases by X time. Same as we learned it in for normality. The same explanation goes here also. Now, molarity is calculated by the formula. A very small change in the formula, weight in grams by molecular weight into 1000 divided by volume of the solution. We'll work out problems based on this. So this is the formula to calculate molarity. See, in case of normality, it is weight in grams by equivalent mass. In terms of molarity, it is weight in grams by molecular mass. That's the only change. You should know the difference between molecular mass and equivalent mass. And also you should know how to find the equivalent mass. So if you know how to find the equivalent mass, then you can work out problems based on these topics. Now, coming to the next method of expressing concentration, molarity and formality. Formality is not dealt with you in few level, and nowhere in higher level also we don't represent a formality. Both molarity and formality express concentration as mole of solute per liter of the solution. Moles of solute per liter of solution. Moles of solute per liter of solution. There is, however, a subtle difference, a small difference between molarity and formality. Molarity is the concentration of particular chemical species in a solution. Molarity is the concentration of particular chemical species in a solution. On the other hand, it's a substance total concentration in a solution without regard to its chemical form. Without regards to its chemical form. What do you mean by that? On the other hand, it's formality. Formality is a substance of total concentration in a solution without regard to the specific chemical form. Now, what will happen if I take NaCl in water? If I put NaCl in water, what will happen? It will dissociate to form Na plus and
Cl
Cl
minus.
minus. As a whole, if you take 1 mole of NaCl in 1 liter, then it's called as what? 1 molar as a whole. If you take this as a particle in 1 liter, then it comes as 1 formal solution. So each particle, that's why they say total concentration. Total concentration. Without regard of its chemical form. Here the chemical form is in the ionic state. We are not bothered about, but total concentration of these particles in 1 liter will be called as 1 formal. Did you follow the difference? Formality, if you don't remember it, that's fine. There is no difference between a substance molarity and formality if it dissolves without dissociating. See, without dissociating, there is no difference. But when it dissociates, now for an example, if you take glucose, C6H12O6, glucose, when you dissolve in water, you get glucose solution. Glucose solution, aqueous solution of glucose. Glucose molecule will not dissociate. Therefore, if you take 1 mole of glucose, this 1 mole of glucose in 1 liter of water, it becomes 1 molar solution, and also it becomes 1 formal solution because no dissociation. But in case of the solute, it dissociates, then there is a minor change. This is as a whole you take, and here we consider the ions. So the molar concentration of solution of glucose, for example, is same as its formality. I just explained it here, and it's been printed also here. Did you understand what is molarity? And did you understand?
Yes, sir.
Now, mole fraction. Did we learn any in this chapter solids mole fraction? Did we learn? No?
No, sir.
No. Okay. Now, what is mole fraction? What is mole fraction? Now, because I'm working, other teachers also teaching somewhere else, get confused. No, that's why. What is mole fraction? You tell me what is weight in grams by molecular mass. Weight in grams by molecular mass will give you what number of moles. Now, solution, when we say it is solute plus solvent, is called a solution. Solution is nothing but a mixture of solute and solvent. Now, what is this mole fraction? Now, mole fraction is, we will define what is mole fraction a little later. Now, solute normally we represent it by a letter NB, number of moles of solute as NB, number of moles of solvent as NA. Now, number of moles is given by the formula weight in grams per molecular mass. I taught you this. We worked on some of the problem also earlier. Now, what is this mole fraction? Mole fraction generally be represented by a letter X. Now, mole fraction of solute is NB divided by Na plus Nb. Now, mole fraction of solvent is given by the formula Na divided by Na plus Nb. So this is how we calculate the mole fraction. What is mole fraction now? It's defined as the ratio of number of moles of a particular component divided by total number of moles. That's called as mole fraction. So if I'm talking with respect to solute, you have to take the number of moles of solute divided by total number of moles of solute plus number of moles of solvent. If you want mole fraction of solvent, then we have to take number of moles of solvent divided by number of moles of solvent plus number of moles of solute, or total moles of solution. Then we'll get what mole fraction. Represent the number of molecules of a particular component in a mixture divided by total number of moles in a given mixture. So this is what is mole fraction. Did you follow what is mole fraction?
Yes.
Yes, sir.
Yeah. Mole fraction, this formula, this is very more. These formulas are very important in the chapter solutions. We will be learning about. And next is also important, molality. It is a property of a solution and is defined as number of moles of solute present in 1 kg of the solvent. So if you take the solvent in terms of liters, you get molarity. If you take solvent in terms of kg, then we call that as molality. So if I take 58.5 grams of NaCl in 1 kg of water, then the solution concentration is called as 1 molal, M-O-L-A-L. So molality is defined as number of moles of solute present in 1 kg of the solvent. See, in molality also considers what? Grams, weight. Since they are considering the weight, temperature has no effect on this weights. Hence, molality is independent of temperature. Not only molality, even mole fraction is also independent of temperature. See, molarity, this changes. Molarity, you can see, inversely proportional to temperature. It's dependent on temperature, inversely proportional. But molality and mole fraction, they are not depending on temperature, because weight remains the same. Whether it expands or compresses, the weight remains the same. Therefore, molality and mole fraction are independent of temperature. Correct? Again, next is it clear?
Yes, sir.
Yes.
Yes, sir.
Next is mass fraction. Mass fraction of a component in a solution is mass of the component divided by total mass. Similar to that. Moles, if you take its mole fraction, if you take weight of component A divided by weight of component A plus component B will be called as mass fraction of A. We will not be using this. We will not be using this anywhere. But still remember, mass fraction of B will be weight of B divided by weight of A plus weight of B. All right, so mass fraction will not be using anywhere, just an information. And demol unit, this also will not be using. It's represented by letter D. The concentration are also expressed in demol units. 1 demol unit represent 1 mole of solute present in 1 liter of solution at what temperature? That's 0 degrees. So far, we never spoke about the temperature. So if 1 mole of solute is present in 1 liter of solution at 0 degrees, then that is called as a demol unit, DEMAL. This also we will not be talking about in exams. Any exams we will not be talking about to you. So these are the formulas which you have to remember to work out the problems. So what I taught you, it is represented by means of a table or a list of formulas. Weight percent or mass percent. Mass of a component in a solution divided by total mass into 100. I taught you, I wrote and explained volume percentage, weight by volume percentage, parts per million, number of parts of a component divided by total number of parts of a component to 10 power 6. 10 power 6 is 1 million. If you multiply by 10 power 9, it becomes parts per billion. Okay, so mole fraction, I told you, it's represented by letter X. Number of moles of a component divided by total number of moles. I told you XA will be NA divided by NA plus NB. Similarly, number of moles.
Excuse me, sir.
Yes. Yes, ma'am.
Sir, will you please send that formula list in chat box?
I don't know how to do it, ma'am.
Is it possible, sir? Or else send it to me through WhatsApp, sir.
I'll do that possibly, ma'am. I'll do that.
Okay, sir. Thank you, sir.
Yeah. So XB will be equal to NB divided by NA plus NB. So this is called as mole fraction. I explained it to you earlier. Now, molarity I defined and I gave you a formula, number of moles of solute divided by volume of the solution in liter. I gave you molarity as a formula. I explained, and molality, small letter m, number of moles of solute in 1 kg of the solvent will be called as molality. This is the ways possible we can express the concentration of a solution. But for you, in second PUC, in 12th class, you need to know how to, in this chapter, we will be concentrating on mole fraction and molality. We'll be working problems using these two formulas in this chapter. So you should be in a position to know how to calculate the moles and how do we calculate the mole fractions and how do we calculate molality. All this two methods of expressing concentration in this chapter will be used. Coming to the next part of the topic, we will learn next part of the topic, that is solubility. Solubility, we learned solubility of a substance is its maximum amount that can be dissolved in specific amount of solvent, that is 100 grams of solvent at a specified temperature. We learned it. Solubility of solid in liquid. This is important. Remember, every solid does not dissolve in a given liquid. NaCl, salt, sugar dissolves readily in water, while naphthalene, anthracene do not. So like dissolves like, you should remember, like dissolves like. What do you mean by like dissolves like? Polar molecule dissolves in polar solvents. Polar molecule dissolves in polar solvents. Now, NaCl has a charge, Na plus Cl minus. Water also has a charge, delta plus. So, like dissolves like, polar molecules will be soluble in polar solvent. See, naphthalene and anthracene are organic compounds. They are non-polar molecules. So, non-polar molecules, non-polar solutes or molecules dissolves in non-polar solvent. Non-polar solvent. Now, when we say non-polar solvent, example for non-polar solvent, benzene is an example for non-polar solvent. Carbon tetrachloride is an example. Chloroform is an example. Alcohol is an example. All these are examples for non-polar solvents. So this naphthalene, anthracene, all that will dissolve in what? Benzene, carbon tetrachloride. For a simple understanding, if you take solvent, you take salt and dissolve it in water, salt will dissolve in water. If you take the same salt and put it in oil, will the salt dissolve in oil? Will the salt dissolve in oil?
No, sir.
No.
No, sir.
Because oil is a non-polar solvent, so it will not dissolve. All right. So factors affecting or which affects solubility. This we will see in a few minutes, and then we'll stop the class for today. Nature of, oh, this is too much. I think nature of solute and solvent. Just now I told you, polar solute dissolves in polar solvent, and non-polar solute dissolves in non-polar solvent. That's why I gave you like dissolves like. So first property. Second, effect of temperature. If the dissolution is endothermic, endothermic means delta H is negative. And the delta H is what? Positive. It's greater than 0, positive. Then solubility increases with rise in temperature. Now, for an example, if you take salt or water, sugar in water, it will absorb energy during the dissolution process. So when you heat, the dissolution process will increase. That is what it means. But if the dissolution is exothermic, if you dissolve, see, this is salt and water. For endothermic, you remember salt and water, sugar and water. Okay. Example for this endothermic process. Now for exothermic, acid and water or a base in water, this is exothermic. When you add acid in water or if you add a base in water, it's exothermic. If the exothermic means delta H is negative, it gives out energy. So for an exothermic reaction, the solubility will decrease with rise in temperature. Because it's exothermic, heat is liberated, some amount of acid or base or water gets vaporized. Therefore, what happens? Solubility will decrease in rise in temperature. So the next property, third property is the effect of pressure. Pressure do not have any significant effect on solubility of solids in liquid. Pressure will have effect or significant effect when the solute is a gas. When gas is dissolved in water, then there will be a effect. But when solid is dissolved in a liquid, pressure will not have any effect because liquid, as these are highly compressible. So in case of pressure do not have any significant effect on the solubility of the solids. All right. So we will learn the other part of the topic, where we can solve some of the problems tomorrow in the class. All right. So shall I stop the class, ma'am? Today? Students, are you there?
Yes, sir. Yes, sir.
Yeah, ma'am. Bye, ma'am. I'll stop the class.
Okay, sir.